In this video for chapter 6.1, we'll be looking at continuing the antiderivative concept graphically, numerically, and algebraically. All right, example number 2 says use the figure below and the fact that p equals 2 when t equals 0 to find the values of p when t equals 1, 2, 3, 4, and 5. So first thing is I'd like to make a chart similar to what we did in our first example with times 0, 1, 2, 3, 4, and 5. And we'd like to find out what p is at those times. Remember, p of t is going to equal the integral from 0 to t of dp dt. Okay? Or we could say of p prime. Okay, so let's take a look at areas under the curve on each of those intervals. I'm going to do that geometrically by just drawing little partitions. So I know the first rectangle has an area of -1, second is -1, the third is -1/2, from 3 to 4 is +1/2, from 4 to 5 is 1. Okay, so they did tell us that p equals 2 when t equals 0. That means for t equals 1, we'll get 2 plus the integral from 0 to 1 of p prime. That will be 2 minus 1, or 1. Continuing that pattern, at 2, the integral from 0 to 2 of p prime will be 2 minus 2, or 0. At 3, the integral from 0 to 3 of p prime will be -2.5. For 4, 2 plus the integral from 0 to 4 of p prime dt. That's 2 plus, it would be a -2 again. And for 5, 2 plus the integral from 0 to 5 of p prime dt is 2 minus 1, which equals 1 again. Okay, we've got symmetric areas there, so that was easy to figure out. All right, and we have found the values of p of 1 through 5. Okay, our next example, example number 3, says estimate f of x for x equals 2, 4, and 6 when the given values of f prime of x and the fact that f of 0 is 50. So I'm just going to start and visualize this. We don't have f prime values on smaller intervals like we did in our last problem where they're 1 unit apart, but we do have 2 units apart. So 0, 2, 4, and 6. We have our f prime values, and I'm just going to go ahead and make a little graph of these. It's not going to be really accurate, but for a visual representation that will help. Okay, and if we think about each of these intervals as creating a trapezoid, we are going to use the idea that we're going to find a trapezoidal sum. Okay, so we know that f of 0 is 50. That's given. That's our initial value. F of 2 will be equal to that initial value plus the area under the curve from 0 to 2 of f prime Okay, so when I look at that, I'm going to say 50 plus the area of that trapezoid. So 1/2 times the height, which is 2, times the sum of each base, which is 17 plus 15. Okay, that's 50 plus 32, or 82. F of 4 will be equal to 50 plus the integral from 0 to 4 of f prime of x dx. Okay, I already know from 0 to 2 is 82. That was my 50 plus 32. So I just need to add on the area of the trapezoid between 2 and 4. 1/2 times 2, the base is 15 plus 10. So that's going to be 82 plus 25. Or 107. Last one, f of 6 will be 50 plus the integral from 0 to 6 of f prime of x dx. Okay, I know that's 50 plus 32 plus 25 plus the area of the last trapezoid, which is 1/2 times 2 times 10 plus 6, or 16. So we're going to get 107. Did I do that correctly? Sorry, nope, that's a 2, not a 6. So plus 12. So 107 plus 12 is 119. Okay. Moving on to example 4. Here we have a particle that moves back and forth along the x-axis. The figure below on the left approximates the velocity of the particle as a function of time. So here is my rate graph. Positive velocities represent movement to the right. Negative velocities represent movement to the left. So just taking a look at this velocity curve or graph, it looks like we're going to be moving to the right, then moving to the left, then moving to the right, then moving to the left. Okay? 1, 2, 3, 4, 5, 6 times. Okay, so my graph's going to kind of look like this when I look at its position. The particle starts at 0.50. Okay, I'm just going to put 5 on the graph, and the graph the distance of the particle from the origin with the distance measured in kilometers and time in hours. Okay, so in the first hour, the object is moving at a velocity of 10 kilometers per hour, which means it's moving to the right 10 kilometers in that hour. So I'm just going to roughly mark out here. My object at time 0 started here at 5, and it's moving to the right until it gets to 15 units from the origin, really, and that's at time 1. Okay, so my object just moved to the right. In the second hour, my object is going to move the same distance, but to the left. So I'm just going to come up above. Actually, I could do a little turnaround, right? Make this my turnaround. I'm just going to come up above, make my line going to the left, 10 kilometers. This is t equals 2. You can also put the little arrows on just to say what's happening with the particle. Okay, it appears that between 2 and 3 we're going to move 10 units to the right, 3 and 4, 10 units to the left, 4 and 5, 10 units to right, 5 and 6, 10 units to the left. So the object is just bouncing back and forth. Units, 10 kilometers to the right, 10 kilometers to the left. And I'll add my arrows to give it direction. Okay, so you could have drawn a graph that just went from left to right and sort of did a little zigzag turnaround at each of those times. Okay. All right, in the next video for section 6.1, we're going to take a look at the integral and some basic rules of the integral and applying those to some examples of finding antiderivatives.